Folks, let us see a Fourier series approximation here. According to the Fourier series, given a waveform, we can always represent it as a DC term and sum of sine and cosine terms. So supposing this is a rectangular wave which is shown in yellow, and I am representing it with just one harmonic which is shown in the cyan. This is not a very good approximation. Supposing now I go and make it 3 harmonics, what you see is you get a better approximation. Now instead of a 3 harmonics, supposing I want to make it 6 harmonics, the approximation still becomes better. And now supposing I want to make it something like 10 harmonics, the approximation still becomes bigger and better. Now what happens is, if supposing I put something like 18 harmonics, the approximation is very good. Now supposing I make it 42, the approximation is very good. Likewise, what we are going to do is we are going to look at what is called a convolution. So you have a sine wave which is going through a system which is given by an exponential transfer function. I can add more harmonics to this particular thing. So I can say sine of 4 star y star t, and I can do sine of 8 star I star t. So now what we have is we have a representative signal. This we are going to pass through a system which is having a exponentially decaying transfer function. So what really happens in convolution is we flip h of n and then we pass it all over x of n, and we calculate the overlapping areas and calculate the area of that particular overlapping region, which becomes a point. And likewise, as we move across the whole signal, we get a whole bunch of points which become y of n. This is easily visible the way I am showing you in this particular demo. So what you really see is x of n has h of n has been flipped, and as it goes across, it calculates the overlapping areas. So now let us see this once again. So I have this h of n, and as I move it all across, there is an overlapping area, so which I can calculate using something like a Simpson's rule or a trapezoidal rule. Now I keep on moving, keep calculating the area, that becomes a point. Keep on moving, keep calculating the area, that becomes a point. Keep on moving, and likewise I get a magenta signal which is nothing but y of n. Welcome folks, I am Arvind Vishnu Matla. In this tutorial, we show visualization of sampling theorem using matlab. Let us take a snapshot of the signal x of t. To sample it, we multiply it with a train of delta functions. These delta functions are shown in red, and they are spaced ts seconds apart. Now for the sake of argument, let us assume that this particular snapshot x of t in frequency domain is represented by a trapezoid going from minus fm to fm. If we take this set of delta functions and we convert them to frequency domain, we are going to get another set of delta functions which are spaced fs distance apart. Now what we are trying to do is we are multiplying two signals in the time domain. This causes a convolution in the frequency domain, and what you will find is this trapezoidal portion of the spectra repeats itself. If we sample at a rate equal to the Nyquist frequency, then the spectra touch each other. So we can get the signal of interest by passing the signal through a low pass filter. However, it is very difficult to make a low pass filter of these kind of characteristics. On the other hand, if we sample at a rate less than the Nyquist frequency, the repeated portions of the spectra overlap each other, and constructive and destructive interference takes place and signal is lost. This is also called aliasing. In general, we sample at a rate greater than twice the maximum frequency, so that we can get a guard band between the repeated spectra, so that it is easy to be able to make a low pass filter and to recover back our signal. Now we show a MATLAB animation of this particular phenomena. Let us assume that the yellow signal on top is the frequency domain representation of the signal. The signal in green is the delta function. Now what we can do is we can do a slow motion convolution to see that the spectra indeed repeats itself. Here what we have done is we are sampling at Nyquist rate, so the repeated spectra touch each other. We can get the signal of interest by appropriately passing this through a low pass filter. Hi folks, let us now obtain the Z domain filter design, and this is a unit circle, and as of now it doesn't have any poles and zeros. So supposing I look at the magnitude spectrum, what you will see is there is nothing in the magnitude spectrum, and if you really see again, there is nothing in the phase spectrum. Now what I do is I will go to the unit circle and add two complex conjugate poles and zeros, let us say at 30 degrees. So now if you can see, there are two poles, two complex conjugate poles at 30 degrees. So supposing I go to the magnitude spectrum, you are going to see a magnitude spectrum. There is frequency on this axis and there is magnitude on this axis. Likewise, there is going to be a phase spectrum. So now if I come back to this unit circle, and because this is h of z, supposing I obtain an h of n here, then I obtain an h of n, which are nothing but filter coefficients. Likewise, now I can do what is called IIR filter design. So what I can do is, supposing I want to obtain a transfer function, and supposing I want a low pass filter, and let me say it's a Butterworth filter. So supposing I have only two edges and I plot the frequency response of a Butterworth filter. This is automatically generated, so it has generated a Butterworth filter of order 8. If you actually go back to the Z domain transfer function, this is the unit circle and this is a set of poles for the IIR filter which we have obtained. Now what we look at the order of the filter. So supposing we go to manual and supposing we put this as 2 and we plot this, what is going to happen is you're going to get a Butterworth filter with a very sharp cutoff. So what has happened is, even though the complexity of computation has decreased here, what really has happened is you are not getting an ideal low pass filter because the cutoff is not very sharp. Now as you increase the order of the filter, say from 2 to 4, what you're going to get is you're going to get a filter with a sharper cutoff. However, this comes at a cost because the complexity of computation increases. Now what you can do is you can actually make it to 8, and you can see, and the moment you go back to h of n, you can get the filter coefficients here. Likewise, you can obtain the response for a FIR filter. So supposing you have an FIR filter and supposing this is in a low pass domain, there is frequency on this axis and there is magnitude on this axis. Now if I go back to the Z domain transfer function, what you will find is you will find only a set of zeros here, and the moment I reset this and the moment I go to h of n, you can find a whole bunch of filter coefficients.